Solve. If a system's equations are dependent or there is no solution, state this. 3x plus 3z equals 0, 2x plus 2y equals 2, and 3y plus 3z equals 3. What I want you to notice is that we can take and simplify this equation by dividing both sides by 3. And it would then be written as x plus z equals 0. This equation we can divide both sides by 2, and it would become x plus y equals 1. This equation we can also simplify dividing both sides by 3, and we get y plus z is equal to 1. And looking at these three, you'll see that it's a little bit easier to solve than if we were to have all of these coefficients other than 1 in the equations. Well, now, let's look and see what we have happening. We have this equation that already does not contain a z. And I have these two equations here where they do contain a z, but we can eliminate it. And if we were to eliminate it, we'll be left with x and y, which we then can solve along with this equation. And so let's do that. What I want you to notice then is we'll multiply this equation on both sides by -1. That result would be negative x minus z equals 0. Then I'm going to write this equation down as is, y plus z equals 1. Add them together, and I have negative x plus y equals 1. Then I will take the second equation, x plus y equals 1, and I already have the coefficients of the variable x opposite in sign. And so if we add the equations, we get 2y equals 2. And therefore, y is equal to 1. We divide both sides by 2. 2 divided by 2 is 1. Well, with y equaling 1, we can go back up to the second equation, which is x plus y equals 1, and substitute y equals 1. X plus 1 equals 1. X is equal to 0. I can go to the third equation, y plus z equals 1. Substitute in 1 for y. 1 plus z equals 1. Subtract 1 from each side to get z equals 0. So the solution is the point x equals 0, y equals 1, z equals 0.